So we've got a rock, and it has a mass of 0.450 kilograms, and it's hurled from a sling as shown. So here's the sling, and it's just a little strip of cloth or twine or rope or whatever with a little pouch there, and you sling this thing around, and then you can throw it at really, really high speed, and a skilled slinger can really throw it very, very accurately too. Much faster than you can throw by hand. Okay, and it's much easier on the arm too. So anyway, so let's go through the details. The sling is a radius of 1.2 meters, and it takes 3 seconds to make 10 rotations. What is the period of each rotation? What is the speed of the rock? And what is the tension force needed? So let's set it up with given. So I'll just draw a quick little sketch here. Here's the radius equals 1.2 meters. The mass is 0.450 kilograms. We said that 10 rotations equals 3 seconds. Okay. And so what do we want to find? For A, we want the period. For B, we want the speed. And then for C, we want the tension force in the sling. So let me zoom out a little bit. So let's solve it. Well, I want the period. So I know that the period is the time for one rotation. So I've got 10 rotations. Oh wait, I want it to be time. So in 3 seconds, I've got 10 rotations. So that's going to be just 0.3 seconds per rotation. We can just drop the per rotation. So 0.3 seconds, and it was that easy. Did you get that? All right, good. Now for part B, well, if I know the period and I know the radius, I can figure out the speed, because speed is the distance per unit time. Well, the distance is the circumference of a circle, which is 2 pi r, divided by the period. So this is 2 pi, and then r is 1.2 meters, and the period is 0.3 seconds. And so V is equal to, there's my calculator, 2 times, my calculator has a pi button, which is really nice, times 1.2 divided by 0.3 equals, and I got 25.13. 13. We'll just round it to 1 meters per second. Well, that's pretty good. I think that's about, I don't know, 50, 60 miles an hour. So that rock's going to hurt. It's going to hurt. Okay, so now part C. Well, what is the tension force? Well, now let's draw a free body diagram of this rock. We've got the tension force like this. Now, in reality, it's also got a little bit of weight, mg, and that's going to bring it down a little bit. But here's what I'm going to do. For this one, I'm going to make it a little bit. I'm going to say that the weight is negligible, or that, you know, if I have to include the weight, it's going to be a really complicated problem that we're actually going to do later on. But it's a little bit too complicated. So we're just going to say that that's the only force acting. So therefore, this tension force is the net force, and that's going to be equal to ma. But it's moving in a circle, so the tension force is equal to m times the centripetal acceleration, which is v squared over r. And now I've got everything I need. 0.450 kilograms. And the speed we calculated to be 25.1 meters per second. We're going to square that. And then we're going to divide by the radius, which is 1.2 meters. And so the tension force equals 0.450 times 25.1 squared divided by 1.2 equals, now this is 236 newtons. Now you're used to thinking of force in terms of pounds. Well, 1 newton is 4.45 pounds, so I'm going to divide this by 4.45. That's 53 pounds of force that that guy has to hold on that sling. That's a lot of force. Those slingers, they were strong. They were strong. Because you have to, it's like 50 pounds going around in a circle very, very fast. So those warriors, the David and Goliath story. I think Goliath was probably the underdog. And the reason I say that is that Goliath had a big sword, okay? And he had, I don't know, I imagine he had a shield. Maybe he had a shield. But the sword only works if you're close in. And David could run fast. He was light. He was quick. He was agile. And he had a sling. And so he had a long-range weapon. And so maybe Goliath should be cut a little slack. Poor guy. I don't know. But anyway, interesting. That is all.